Picture a high-tech radar mapping system in action. Its job is to read a massive, unstructured spatial grid made entirely of ones and zeros, representing land and water. The system has a specific, strict objective. It must accurately count the distinct clusters of landmasses separated by these oceans of empty space. The most obvious way to do this is to deploy a linear scanner. It simply sweeps across the board, left to right, top to bottom, and tallies every piece of land it hits. But this naive linear sweep fails almost immediately. It overcounts the islands because it treats every single coordinate of land as an entirely separate landmass, even if they are directly connected. The logical fix is to program the scanner to check the immediate surroundings. When it finds land, it looks at the adjacent coordinates to see if they belong to the same cluster. This introduces a fatal error. The scanner checks the neighbor, sees its land, moves to it, and then checks its neighbor. Since it doesn't track where it came from, it gets caught bouncing back and forth between two adjacent coordinates forever. This infinite loop creates a logic lock. The system hangs as it exhausts the call stack, and the process terminates. A spatial grid is ultimately just a sequence of numbers, until we overlay a mathematical structure. We have to treat this grid as an implicit graph, teaching the system how to remember the shapes it has already explored. Before we can safely run an advanced spatial algorithm, we have to establish boundary defenses in our code environment. The very first line must be a critical safeguard, the empty grid check. If we skip this check and pass in a null or empty matrix, the program attempts to measure a void. This triggers an immediate out-of-bounds error or a null pointer exception, halting the program. A simple return protocol fixes this. It checks if the grid is empty right at the start, and if it is, it immediately aborts the mission and returns 0, protecting the larger system. Even the most sophisticated algorithmic logic fails if the foundational architecture cannot survive unpredictable edge cases. With the safeguards in place, the global scan restarts. It sweeps linearly across the grid, row by row, until it strikes the very first piece of land, and pauses. At this exact coordinate, we initiate a depth-first search. This is a secondary protocol that acts like a spreading digital probe. It treats the grid as a graph, recursively pushing to its top, bottom, left, and right neighbors. Strict mathematical parameters act as invisible walls. If the index exceeds grid dimensions, the vectors hit the perimeter and instantly terminate. To prevent the infinite loop, the protocol uses a memory-efficient optimization by modifying input data in place. This syncing mechanic actively overwrites every piece of land the probe touches, changing ones to zeros and erasing the island as it explores. Once the probe hits surrounding water or a boundary in all directions, the recursion stack unwinds. It finishes its job and hands control back to the global scan. By mutating the terrain, depth-first search maps the entire connected cluster with O of 1 auxiliary space, eliminating the infinite loop entirely. The global scanner now resumes its linear path across the grid. Because the island we just explored was converted to zeros, the scanner glides frictionlessly over the newly created empty space. We increment our total island count by 1. The system avoids checking those same coordinates twice and finishes its tally in linear time. This approach minimizes memory usage. Because we reuse the input grid for tracking, we don't need a separate matrix to log which nodes we've already visited. But there is a hidden cost to this efficiency, known as destructive mutation. In a real-world concurrent software architecture, modifying the input has side effects. Another process might urgently need that original map data, and because we sank the islands, that data is now gone. The production-ready alternative is to allocate extra memory to build a separate tracking matrix. This allows us to log our progress and identify visited cells while preserving the original terrain. Choosing between these two methods requires weighing the performance gains of mutating data against the requirement for data persistence.